Welcome to this session on homomorphic encryption. So the first talk will be on a paper whose title is Threshold Linearly Homomorphic Encryption on Z over 2 to the KZ. And the speaker will be Ida Tucker. So Ida, the floor is yours.
Hi, thank you for the introduction. So yeah, I'm going to tell you about a scheme that we developed, which is for threshold linearly homomorphic encryption, where the message space is Z over 2 to KZ. And this is joint work with Guillaume Castagnos and Fabien Laguillons. So I'll start by explaining at a high level what threshold public key encryption is. So the idea is it's just a public key encryption scheme where the secret decryption key is shared according to some decryption policy among various decryption servers. And as any public key encryption scheme, the public key is public. And so anyone can encrypt a message M with this public encryption key to produce a ciphertext of M. So the ciphertext here is the red M. And then in thresholds public key encryption, we have a partial decryption where each server is going to use their partial decryption key in order to compute partial decryption shares. And in order to recover the initial plaintext, we have another final decryption protocol, which is public, so anyone can perform this. And if you have a number of ciphertexts from secret keys which satisfy the decryption policy, so we'll say they're part of the qualified set, then combining these ciphertexts will allow you to recover the message. And if the secret keys don't satisfy the policy, the decryption will return an empty set, not an error, it should be an empty set. If we want this threshold public key encryption scheme to further be linearly homomorphic, I mean, this means that one should also be able to perform, by performing operations on the ciphertext, you can perform linear operations on the underlying plaintexts. So we have two efficient algorithms, one which, given a ciphertext of M and a ciphertext decrypting to M star, you can produce another ciphertext which will decrypt to M plus M star. And an algorithm called eval-scal, which takes a ciphertext which decrypts to M, a scalar alpha, and produces a new ciphertext which will decrypt to alpha times M star. And linearly homomorphic threshold public key encryption on Z over 2 to the KZ is basically the above, but where the message space is Z over 2 to the KZ. So we can encrypt any message modulo 2 to the K. And the interesting thing here is that these homomorphic
Ida,
operations...
we can't hear you anymore.
Oh, shit. Okay.
I can hear.
Can you hear me?
Yes.
Okay, great. So the interesting thing about having an encryption modulo 2 to the KZ here is that the homomorphic operations that we do on the ciphertext under the hood on the plaintext, they're performed modulo 2 to the K. Okay, and so why is this interesting? So there are various applications, but I'm going to just describe one of them, how this can be applied to multi-party computation modulo 2 to the K. So briefly, the idea of a secure multi-party computation is that we have like various parties. Here we have 4. They all have secret inputs, say x1, x2, x3, and x4, and they all want to compute a function of all of their inputs put together, but they don't trust the other parties and they don't want to reveal their secret inputs to the other parties. So one way of doing this would be having a trusted party like this angel here, and all the parties send their secret inputs to this person that they all trust. the trusted person computes the result of the function and sends it back to everyone. But of course, in real life, angels are kind of hard to come across. And so the idea of secure multi-party computation is achieving the same goal, but without a trusted party. So all the participants should keep their secret inputs secret, but at the end of the day, they all want the result of this function on their private inputs. And there's been a lot of interest recently, I mean, fairly recently, for multi-party computation modulo 2 to the k. And this is mainly because on standard CPUs, integer arithmetic is performed modulo 2 to the k. So for instance, 32 or 64-bit chips. And if we have secure multi-party computation modulo 2 to the k, we mirror this design. And it means that one has simplified implementation of these MPC protocols. We don't need to perform modular arithmetic or compensate for modular reductions. And it also means that programmers that are implementing these protocols can use optimizations for CPUs directly. And so how does one go about building multi-party computation modulo 2 to the k? Well, there's a kind of common blueprint which is used to build maliciously secure multi-party computation protocols. It divides the process in two phases. So we have a pre-processing phase, which is offline. So this means the participants can do it without knowing the inputs that they're going to use for their computation, or even the function that they're going to compute. And it's slow. And the idea is to compute many shares of triplets of the form A, B, A, B, where A and B are random in Z over 2 to the KZ. And these triplets are then going to be used to speed up the fast online phase. And they're basically used as masks during this, this protocol. And so this online phase is fast and information theoretically secure. So we'd like a way to improve the slow phase, the pre-processing phase, because the online phase is already very efficient. Techniques that were used in the past are notably oblivious transfer, which was used in SPDZ2K to create these triples. So oblivious transfer yields a fast solution, but the bandwidth consumption is quite high. Then in Overdrive 2K, they use somewhat homomorphic encryption. So this does improve the bandwidth consumption, but the actual protocol itself is quite complex. And so implementing it for developers is quite hard, and there's more risk of there being mistakes. And then another solution, which is much closer to what I'm going to talk about, is one by, they develop in Monza, which uses linearly homomorphic encryption modulo 2 to the k to produce this raw material. And in particular, the scheme that they use is the Joly-Libert encryption scheme, which is linearly homomorphic and has a message space of Z over 2 to the KZ, which is great. But there's no known threshold decryption for this scheme. And under standard assumptions. And in particular, this means that in Monza, they only have a two-party MPC protocol. And because each party has their own secret and public key, instead of sharing the decryption key, they need to use zero-knowledge proofs to prove to other parties that the other party that what they're doing is correct. And so obviously these zero-knowledge proofs have a negative impact on bandwidth. And so the efficiency gains that one would have expected compared to, say, speeds 2K are not as big as we would like. And so in our work, what we do is we create a threshold linearly homomorphic encryption scheme with a message space Z over 2 to the KZ, which is exactly what we need to fill this gap and efficiently produce these triples. and save on bandwidth. So I'll first kind of give an abstract view of the tools that we use to build our construction and how we build our scheme from these abstract tools. And later on, I'll explain briefly how we realize this framework from class groups. So the framework is quite similar to that of Castaños and Laguiomi from CTRSA 2015. We have a cyclic group G of order S times 2 to the K, where the GCD of S and 2 to the K is 1. We have a subgroup of G called F, which is the 2 to the K, which is 2 to the K roots of unity of G, and is of order 2 to the K. And there also exists an efficient algorithm for computing discrete logarithms in F. So it means computing X given F to the power X. And finally, we have another group H, which is the subgroup of 2 to the K powers of G and is of unknown order S. And it holds that G is isomorphic to the direct product of F and H. And finally, even though we don't know the order of S, the order S, which is the order of H, and hence the order of G is also unknown, we do know an upper bound S tilde for S. And the security assumption that we use in this framework is a hard subgroup membership assumption, which essentially states that if one samples a random element from the subgroup H or a random element from the subgroup H multiplied by the generator F raised to the power some invertible elements modulo 2 to the K, then both elements should be computationally indistinguishable. And so to build a public key encryption scheme on Z over 2 to the KZ from this, the scheme is fairly simple. It looks like L gamma in the exponent. So we sample the secret key from a distribution which is close to uniform, which induces a distribution close to uniform over H. And the public key is just the generator of H raised to the power of the secret key. To encrypt a message M in Z over 2 to the KZ, we sample a random element R in this distribution DH. And then we compute a first ciphertext element, which is H to the power R, and in the second part of the ciphertext, we encode the message in the exponent of the generator F, and we mask this with the public key raised to the power R, and the ciphertext is both elements C1 and C2. Finally, to decrypt, one multiplies the second part of the component C2 by C1 raised to the power minus SK. And this should be equal, if this is a correct ciphertext, to F to the power M. And so here we check if the resulting capital M is in the subgroup F. If not, then the ciphertext is badly formed and the ciphertext is rejected. And if so, we return the discrete logarithm in base F of capital M, which, as I mentioned earlier, is efficiently computable. And so it's quite easy to see that this scheme is also linearly homomorphic. In order to add plaintexts which are underlying to ciphertexts, you just multiply the two ciphertexts component-wise and then re-randomize the resulting ciphertext. And similarly, to perform scalar multiplication, one just raises each ciphertext component to the power of the scalar alpha and then re-randomizes the resulting ciphertext. For security, I'm basically going to follow a kind of game-based approach. So I'm going to perform little changes to the original encryption scheme, which I'm going to justify are unnoticeable to anyone who's looking at the scheme from an outsider's perspective, who doesn't know the secret key. And then I'll get to a point where the message is statistically hidden. And since if we have a simulated game, a simulated like encryption scheme where the message is statistically hidden and that's undistinguishable from the real scheme, then we'll be convinced that the real encryption scheme is secure. So the first change that we do from our original encryption scheme is instead of sampling the secret key from a distribution which induces a uniform distribution over H, we're going to sample it from a distribution which is close to uniform modulo S times 2 to the K, and so induces a distribution uniform over G. And because the order of H divides the order of G, S divides S times 2 to the K, this change is unnoticeable given only the public key and the rest of the scheme. The next change we do is purely conceptual. So we compute C2 in a different way. Instead of computing the second part of the ciphertext as F to the power M times PK to the power R, we're going to compute it as F to the power M times C1 to the power SK. But these are actually exactly the same. They're just computed in a different way because C1 is H to the power R and PK is H to the power SK. So PK to the power R and C1 to the power SK are the same thing. The final change we do is we sample an extra element U in Z over 2 to the K, in the invertibles of Z over 2 to the KZ, and we multiply the first part of the ciphertext, H, which was H to the R, by F to the power U. And so now we can notice that the first part of the ciphertext in our previous game and the first part of the ciphertext now are so basically the two elements that one tries to distinguish in the HSM2K problem. And so if this HSM2K assumption holds, which we assume it does, we're ensured that this change is indistinguishable. So now we're in this like final simulation game, which we've established is like indistinguishable from the real encryption scheme. And here we can see that the information that can potentially be leaked on the message is contained in C2, which is F to the power M plus U times SK times PK to the power R. I've just rewritten this by developing C1. And so an unbounded adversary would at most be able to deduce from this the value of M plus U times SK modulo 2 to the power K. And here the secret key SK was sampled from a distribution which was close to uniform modulo S times 2 to the K. So even though the value of SK is information theoretically fixed modulo S, because of the public key, which reveals H to the power SK, the value of SK remains close to uniform modulo 2 to the K because S and 2 to the K are co-prime, and 2 to the K divides the order of G. So we have SK, which is close to uniform modulo 2K. We have U, which is chosen to be invertible modulo 2K. And so the product of U times SK is close to uniform modulo 2K, and so perfectly masks our message, well, statistically masks our message M, and this is what we wanted to prove security. And finally, to make this scheme, to obtain a threshold decryption for our scheme, we just noticed that the decryption key SK is only used in decryption for exponentiation to this secret key in the group of unknown order H. And so we use linear integer secret sharing to share the decryption key over the integers. And so our resulting scheme allows any access structure for the decryption policy, and in particular threshold decryption. And so how do we realize this abstract framework from class groups? Well, we start from the original CL framework. In their framework, they provide a very similar abstraction, the main difference being that the subgroup F, which encodes messages, is of prime order Q. In their work, they have two class groups, one with the fundamental discriminant delta K, which is set to minus P times Q, where P and Q are prime, and the class group of non-maximal order of discriminant minus P times Q cubed. In this setting, we can create a surjection between the class group of the maximal order and the class group of the the class group of the non-maximal order and the class group of the maximal order, and whose kernel is of order Q, and we're going to set the subgroup F to be this kernel of order Q. And it would be great if we could just plug Q equals 2 to the K and get our resulting scheme, setting, but that unfortunately doesn't work for various reasons. But the main problem is that if you know the factorization of the discriminant, which is the case in the original CL, you can compute square roots and you can decide if elements are squares. And if that's the case, our hardness assumption, HSM2K, doesn't hold at all. It's completely broken. So we need to have a setting where computing square roots is hard. And so that means that the factorization of the discriminant cannot be known. And so we build our discriminant from an RSA integer n. But we can't choose any n, we have to be careful. In particular, if we're looking into the genus theory associated to class groups, one can see that some genera can leak information on discrete logarithms. And so we have to carefully select the discriminants and hence the RSA integer n, which will allow us to securely work with the group of squares of the class group. Okay, last but not least, performance. So we did do an implementation in our paper, but since then, Bouvier, Castaños, Imbert, and Laguillaume have implemented a library from scratch in C and C++ called Bicycle, which improves our timings. So I'm providing these better timings. Yeah, as you can see, decryption is for like a message space 2 to the 64 and 128 bits of security. Our decryption is only like 40 milliseconds, which is very efficient. So yeah, that's basically it. Thank you very much for your attention. And if you have any questions, I'd be happy to try and answer them. Or maybe there's not much time for questions because I went over time.
Hi, can you hear me? Hello? Hello? Okay, I guess you can hear me. Okay, thanks. Okay, hi, I'm Zeyu Liu. Today I'm gonna present large precision homomorphic sign evaluation using a few TFHE bootstrapping. This is joint work with Daniela Michancho and Yuri Polyakov. Let me start by some background information. So what's functional or programmable bootstrapping? Basically means that we can evaluate a acyclic function through lookup table for free, while also performing some bootstrapping over some LWE ciphertext. This is first introduced in DM15. And it has two requirements or two constraints. The first one is that it requires the function to be negacyclic. And what does it mean by negacyclic? Basically means that for an input in ZQ, the function needs to satisfy that f of x equals to negative of f of x plus q over 2. The second constraint is that it can only evaluate functions over messages with up to k bits of precision, and usually k is equal to 5 or 6. The reason is that its runtime is exponential in the number of bits, and for the number of bits beyond 5 or 6, the runtime will become quite impractical. And we will use this notation for bootstrapping. So basically, we use boot for some function f over x, and it will output the ciphertext that's encrypting f of x for some negacyclic function f from zp to zq. And this p and q can be different, but for simplicity, you may assume that p and q are the same number. There are two bootstrapping methods available now. And the first one is a few introduced in DM15. It efficiently supports arbitrary secrets, but the bootstrapping key size is relatively large. And the second is TFHE, introduced in CGGI16. It provides better runtime performance for small secrets like binary or ternary secret, and the bootstrapping key size is much smaller. Please see MP21 for a more detailed comparison. And we use this functional bootstrapping methods as a black box. So either of the two work for us, it serves the exact same functionality. There's another bootstrapping method that's recently developed and can be applied as well, but it's not included in this work, but because the paper is published before the new method is proposed. So the main results of our work. So at a very high level, we introduced some new tools to this few TFHE line of work to make the schemes more powerful. More specifically, first we introduce some large precision comparisons. So why comparisons? Comparisons are widely used in machine learning, like in CNN inference or DTT training, and in data science. And comparisons are usually considered hard for FHE schemes, and privacy-preserving ML or DS is an essential case for FHE. Currently, the runtime for this is exponential with the bits of precision, and we want to make the runtime linear scale. The second tool is more general and more powerful. We provide the way to do a large precision arbitrary function evaluation. As mentioned before, now it only supports for negacyclic function and only supports for small precision. We have implemented our schemes, and the implementation is open sourced in OpenFHE and Palisade libraries. So let's start from some high-level ideas. One observation we have is that the comparison is equivalent to sign evaluation. To compare two numbers A and B, we just need to find the sign of A minus B. And another observation is that the sign evaluation is equivalent to computing the most significant bit. Computing the most significant bit is the central part of few or TFHE bootstrapping, but as mentioned, that it only supports for up to, say, k bits. Therefore, our key technique is that we try to remove the large numbers digits gradually. For example, if you take a look at this 18-bit number, we just remove the last 6 bits and then remove the middle 6 bits. When we have only 6 bits left, we can perform some few or TFHE bootstrapping to extract the most significant bit. So to do large precision comparison, we first used a floor function, first to round down the last k bits. So if we have this 12-bit number, we just make the last 6 bits zeros. And then we divide this result by 2 to the k, where 2 to the k is equal to 6 here, using modular switching, and this will make this 12-bit number into a 6-bit number. We cannot directly use modular switching to round down the original 12-bit number because modular switching is performing a rounding instead of flooring, which will cause errors for some values near the boundary. And then we repeat this procedure for each digit as mentioned before. After there are at most like k bits left, we can perform a regular few bootstrapping to extract the most significant bit. This one question remains is that the floor function is not negacyclic. So how can we evaluate it? So let me ask a question. What is really a floor function? A floor function is basically we give you a number and you make the last k bits 0. So we achieve this functionality by invoking the functional bootstrapping twice with 2 different negacyclic functions. We first clear the most significant bit of the last k bits. So for an 8n-bit number from B1 to Bn, the last k bits are from here to here, and we just clear the most significant bits of the last k bits. We clear this by using the follow function. You can double check that this is indeed negacyclic. So this can be achieved by invoking one functional bootstrapping with this function. And then we clear the rest of the k-1 bits, i.e. the bits here. And we achieve this by using the second function here. And again, you can double check this is indeed negacyclic. This is our pseudocode. As mentioned before, for the floor function, we first use the F0 to remove the most significant bit of the last k bits, and then we used F1 to remove the last k-1 bits. And we process this, we use this floor function digit by digit until we have only log q bits, i.e. the k bits left, and then we can use the original few or TFHE bootstrapping to extract the most significant bit. Now let's talk about the more general tool, the arbitrary function evaluation. Let's start with some small plain text module. The first constraint we need to get rid of is that the few or TFHE bootstrapping will require the input function to be negacyclic. So can we make the function arbitrary, like remove the negacyclic property requirement? Similar to the floor function, we can use 2 functions to achieve this functionality. We first remove the most significant bits of the input. Sorry. And then for the rest of the bits, we'll be able to evaluate an arbitrary function upon. After removing the most significant bit, we can just use a negacyclic function to with k bits to represent an arbitrary function with k-1 bits. But then how about the most significant bit? It turns out that we can raise the modulus from q to 2q, then it will introduce a random most significant bit to the input. So basically with a k-bit input, we will raise the modulus to from q to 2q, and then the input will become k+1 bit, and then we remove this redundant random bit, and then we can perform a negacyclic function, an arbitrary function evaluation using the original few or TFHE bootstrapping. Here's the pseudocode. This is the function we use to remove the most significant bit. Again, you can check that this is indeed negacyclic. And for the input function, we'll use a negacyclic function to represent it. But since the most significant bit is clear to 0, one of the branches will not be used at all. And here we first remove the 1 bit, and then we evaluate this arbitrary function on the input. So now let's talk about how can we make this the small precision into large precision. We do this first by breaking a large precision ciphertext into several small ciphertexts. This is done through what we call a ciphertext decomposition or homomorphic digit decomposition. This can be achieved by calling the large precision sign evaluation, as I mentioned before, and we just need to collect the bits removed. If you recall that in the large precision sign evaluation, we need to remove k bits at a time. We just need to collect the k bits. Then we end up with several small ciphertexts that each encrypting k bits of message. This essentially has the same cost as the large precision sign evaluation. Then we can evaluate each small ciphertext sequentially using a chain ship method or tree ship method. Both of these methods are first introduced in GBE 21. For the chain ship method, as you can see, it's like a chain. So if we first use a few functional bootstrapping to evaluate C0, and we will get a result out. This carry result will be processed with the second input, and together it will be evaluated using the second functional bootstrapping, and sequentially we will get some results. But this method is relatively restrictive because not all functions can be expressed in this way. So they have the second method, which is the tree method. The tree method basically is saying that for the first input, instead of outputting a LW ciphertext, it outputs some lookup table. And this lookup table will be used to evaluate the second ciphertext and so on and so forth. This is much more general and much more powerful. All of the functions can be expressed in this way. But the catch is that the runtime will be much worse than the first method. But to sum up, using the ciphertext decomposition, we can use these two methods to achieve arbitrary function evaluation over large precision. There are two concurrent and independent works. Both of the approaches use the observation that -1 times -m equals to m, and the extraction of most significant bit using few TFHE bootstrapping. Both of these algorithms use multiplication and requires at least 2 bootstrapping invocations. CROT21 uses a BFE-like multiplication, and KS21 uses a GSW-like multiplication. And we will omit the details. We refer the audience to those 2 papers to find out the details. But our approach does not require any multiplication and can be instantiated using only addition and few TFHE bootstrapping. Here's an asymptotic comparisons. As you can see, the noise growth, our noise growth is the smallest, and also we have less number of bootstrapping evocations compared to KS21, and the same compared to CROT21. Now let's talk about the experimental result and applications. We have implemented our algorithms in Palisade and OpenFG libraries, and we evaluate the large precision comparison for precision ranging from 5 bits to 21 bits. The result is single-threaded and with TFHE bootstrapping using G++ 9.3.0. Here's the result. I will not go into detail of all of them, but as you can see, the runtime basically scales linearly with the number of bits. We have also implemented the arbitrary function evaluation just to prove that it indeed works for only small precision. We have also applied our techniques to heaviside activation function over 256 slots by using CKKS few TFHE scheme switching technique. More generally, one can use our large precision comparison to perform an encrypted branch evaluation. There's another important line of work that uses CKKS to perform comparisons, and those results are all based on polynomial approximation of the sign function. And I would like to at a very high level, we'll compare those two lines of work, but the detailed comparison, of course, may benefit from a more detailed survey paper. So for state-of-the-art CKS-based comparisons, it takes roughly 30 seconds to compare for 64K slots, while our method is 6 seconds for one slot. So if the number of comparisons needed is very small, our method will be faster. Also, our method is easily parallelizable, while CKK supports only limited parallelization, which means that if we have multiple cores, that even if the number of comparisons are larger, our method may still be preferred. Another point is that higher precision of CKS method, like 50 bits, can be very hard to support because the log Q can easily exceed. The log Q is the ciphertext modulus for CKS schemes, can easily exceed like 3000, and this will also cause the ring dimension to grow, which will cause the performance to be much worse. Also, to perform like a 50-bit precision comparison, the scaling factor of CKKS also needs to be increased from 64 bits to 128 bits, which will further reduce the performance. According to our benchmark using Palisade, it can be as bad as like 8 times slower. And of course, our method is much simpler to implement and use. And if multiple invocations of sign evaluation is needed, CKKS-based method needs bootstrapping in between, which will further reduce the runtime, while ours do not. There are, of course, some challenges and potential promising and interesting future directions. The main bottleneck here for the runtime is the TFHE or few functional bootstrapping. Each comparison has to be done separately. There's no CRT packing support, and performance can be improved only by parallelization and like using multiple threads or GPU-like parallelization. So one very interesting question that can be asked is that, can we develop other methods for functional bootstrapping with better efficiency? And can we leverage BGB or BFE bootstrapping for this? Let me finish today's talk with some conclusions and remarks. So first, in this work, for the few TFHE line of work, we have provided so far the most efficient large precision comparison and more generally large precision arbitrary function evaluation. And moreover, this algorithm can be combined with CKKS. One can use CKKS for polynomial function evaluation and use our algorithms for non-polynomial function evaluation, like comparisons or like activation functions and so on. Of course, this will need some switching technique between CKKS and few, and this can be done from using CKKS few TFHE scheme switching technique, first introduced in Kimela paper and later improved in Paxos. And OpenFHE is planning to include this scheme switching technique, scheme switching feature in version 1.1. So after this is published, or one can simply use and as mentioned, that our algorithm and also CKKS are both included in OpenFHE already, which means that if this feature is public, one can simply use the OpenFHE library to perform what I mentioned above to incorporate our algorithm with the CKKS scheme. And these are the references, and that's pretty much it for my today's talk. Thank you all very much, and I'm open to take questions.
Are there questions from the audience or online? No, I don't see any question. Okay, so let's thank the speaker again.
Thank you.
Is in person. Do we have the speaker? Ah, excellent. Please go. So the next talk is on the eval round algorithm in CKKS bootstrapping, and the talk will be given by Seong-Hak Kim.
Thank you for introducing. My name is Seong-Hak Kim, and I'm going to introduce our paper of eval round algorithm in CKKS bootstrapping. So let me start by giving a brief overview of this talk. The main topic is CKKS, which is a representative homomorphic encryption scheme, which is widely known for its ability to deal with real numbers. CKKS bootstrapping is later suggests operation, which recovers modulus of a ciphertext, so it can be evaluated arbitrary times. So a problem of this CKKS bootstrapping is it is an operation of recovering the ciphertext modulus, but it consumes modulus at the same time. What I mean is that it is another big combination of addition and multiplication. So it consumes modulus and it directly determines how many evaluation depths are left after after bootstrapping. So we are focusing on reducing such modulus consumption by proposing a simple yet effective variant of CKKS bootstrapping, which consumes less modulus and which can be implemented with a negligible cost on the existing conventional bootstrapping algorithm implementation. The contents will be given as follows. I'll start by giving a background, focusing on this modulus consumption of CKKS. And as our algorithm is constructed tightly on the conventional bootstrapping algorithm, I'll spend some time on reviewing the conventional algorithm and I'll introduce the eval round algorithm. In this talk, I'm focusing on delivering high-level ideas, so please check details on our paper. I'll not explain the whole concept of homomorphic encryption, but homomorphic encryption scheme can be characterized with three operations, namely encryption, decryption, and a method to evaluate our desired function on homomorphically on a ciphertext. So let me look close in the case of CKKS. CKKS provides three spaces: message, plaintext, and ciphertext, with encoding and encryption. So focusing on the plaintext and on the ciphertext, these are constructed on the well-known problem called RLWE. So the CKKS can utilize its homomorphic structure, which is constructed on the polynomial with finite field coefficients. With this RLWE problem, the encryption of the plaintext is given as the equation below. On focusing on the message and plaintext, the encoding and decoding map is defined by discrete Fourier transform. It is natural to define the map by this, since they are polynomials and vectors. And then one more thing on the CKKS is that the message are complex vectors and plaintext are integer polynomials. So we have to scaling up to encode the message and scale down to decode the plaintext. So in short, the encoding and decoding map is given as the below. One problem arises from the scaling up. It is the size of encrypted plaintext is growing by each multiplications. In brief, suppose the plaintext 1 is scaled up by scale factor 1, delta 1, and plaintext 2 is scaled by delta 2. Then the simple multiplicated result will be scaled by delta 1 multiplied by delta 2. So if we naively execute the evaluation circuit, the size of the encrypted plaintext will grow exponentially. Actually, main feature of CKKS is dealing with dealing with the size of encrypted plain text efficiently, it supports the operation of rescaling to maintain the size of encrypted plain text, which is an operation of dividing the ciphertext modulus and the encrypted plain text at the same time. So rescaling deals with the size of encrypted plain text in exchange of consuming modulus. And the amount of modulus consumed is exactly the same as the encrypted plain text has scaled down. It is often visualized by the diagram on the right side. So we have some plain text of size M1, and we have another plain text of size M2. Then the multiplicated result will be size of M1 multiplied by M2. And we just cut out the LSBs by rescaling. And the cutout amount is equals to the modulus consumption. Such a rescaling is a brilliant way to deal with the size of encrypted plain text, but still there is a challenge. The challenge of all the CKKS is that through evaluating the circuit, the ciphertext will eventually run out the ciphertext modulus, so it cannot be evaluated any further. So bootstrapping is later suggests to recover the ciphertext modulus. So we just bootstrap the ciphertext at the bottom modulus and continue the evaluating ciphertext. So it completes the CKKS at the fully homomorphic encryption scheme. The problem we are focusing on this CKKS bootstrapping is that it consumes modulus. Actually, the first step of bootstrapping is projecting to the higher modulus. So its modulus is already recovered, but we have to adjust the value of projected ciphertext to the original message. So it consumes modulus from that. So after bootstrapping, the ciphertext modulus weight goes down from the fresh modulus. And the size of the ciphertext modulus after bootstrap directly determines the possible evaluation depth till another bootstrap. So we'll go on reviewing the conventional bootstrapping algorithm. The input and desired output of bootstrap can be defined as shown. So input is the ciphertext which is encrypting a desired plain text, but it is on the bottom modulus. We desire on bootstrap output to be on another ciphertext which is encrypting the same plain text, ignoring the encryption error, but on the greater ring of greater ciphertext modulus. So the conventional bootstrapping algorithm is proposed with 4 steps, namely mode rates, coif slot, even mode, and slot coif. So I'll go on briefly explaining each steps. The first step of mode rates is just projection. Note that ciphertext of bottom modulus is also an element of higher modulus. So we just regard it as another modulus on the ring of higher modulus. Recalling the definition of decryption, we can know that the decrypted plain text of moderated ciphertext is somewhat deteriorated with Q0i term. So the problem becomes to remove this superfluous Q0i term from the deteriorated ciphertext and recover the original encrypted plain text. The following steps deals with it, but there is a problem that we want to manipulate the coefficients plain text directly, but we have only methods for manipulating and encrypting messages. It's also known as slot. And the operations deals with encrypted message are plain homomorphic operations. But we can think of sending those coefficients to slots by applying homomorphic encoding. So recalling the definition of encoding, this is a linear map, so we can just homomorphically evaluate this. So after sending those coefficients to slots, we just deal with the PT plus Q0R term by homomorphic evaluation and recover the space by applying inverse of the coefficient slot. So on the following step, we apply homomorphic operation on PT plus Q0I to compute the original encrypted plain text by applying modular reduction. This modular reduction is simply approximated by sign function, so it is not hard to approximate this function. And there have been various approaches to enhance this. But I will not cover those approaches because our suggestion can be applied on any of the implementations of Eber mode. So I'll go and explain Eber round algorithm. The construction of Eber round algorithm is consisted of two minor modifications on the conventional bootstrapping algorithm. The first modification is on the coefficient slot step by alternating it to its variant, which is computing imprecise result in exchange of consuming less modulus. By changing the step of coefficient slot to coefficient slot sharp, we get an erroneous result. But on the following modification of alternating Eber mode to Eber round, we can deal with the error effectively. So we'll look how can it be done. The first modification is coefficient slot, which is can be done by just adjusting parameter. In detail, we use lower scale factors to scale up less on encoding IDFT metrics. So looking on the coefficient slot, which is an homomorphic matrix multiplication, so it is an inner product with encoded diagonals and rotated plain text. So what I want to point out is that it is encoding such diagonals. By adjusting its scale factors, we can adjust its valid bits or precision of the IDFT coefficients. So by using lower scale factor, we can expect the imprecise result. But at the same time, because the rescaling consumes modulus as much as the scale factor scaled down, we consume less modulus, which is an desired behavior of our algorithm. So after taking advantage of consuming less modulus, we have to deal with such error by alternating Eber mode to Eber round. Eber round is semantically, it is an homomorphic evaluation of modular rounding, and it can be formally defined by identity subtracted by Eber mode. So simply defining by this equation has, since Eber mode is a homomorphic evaluation of modular reduction, the identity minus Eber mode is mapping to the value to the closest multiple of the wanted integer. So applying eval round can completely alternate the existing step, and the proof is given as below. So the left side is the step 2, 3, 4 of the conventional bootstrapping algorithm. And we utilize the homomorphic structure of the slot coef and eval mode as coef to slot. So if we rewrite the eval mode by identity minus eval round, the identity can be evaluated separately with eval round. So we get the equation of identity minus eval mode slot coef eval round coef to slot bootstrap is the same, computes the same result from the conventional one. Although the eval round stack computes the same result of the conventional one, there is an advantage of that eval round is much more stable to the input error. So it can be directly seen that as the input changes, the modular reduction, the result of modular reduction changes directly, but modular rounding does not. So it is much more stable to the input error. So we can take advantage from the stability to consume less modulus. By applying the algorithm described so far, we evaluated as on the table. We developed our own CKKS code to test the algorithm on practical parameters. So we give the size of message and bit size of modulus with practical means. But we maintaining the precision, we obtained less modulus consumption by 84 bits. So it is sufficient amount to increase evaluation depth after the bootstrap. It becomes more and more effective when it is applied on the parameters with heavy bootstrap circuits. So the original evaluation depth is small. The great advantage of this algorithm is that it does not require such assumption or effort to evaluate or implement. So it is easy to upgrade on the original bootstrapping algorithm, and it is superior to the existing one. What I want to point out is that the hard thing is to set the scale factor of coef to slot. Hence, this determines how much error on the coef to slot shop step is occurred. But the firm setting on the scale factor will be described on the paper. So summing up, we have implemented, so we have suggested a novel algorithm of conventional bootstrap, novel variant of conventional bootstrap to consume less modulus, and it is to implement on the conventional bootstrap implementation. Thank you for listening.
Are there any questions?
Thank you for your presentation. I have a question about eval round. So can you show again the definition of eval round? So Okay, this is the second question. Anyway, so what I don't know is that I don't know about the role of identity function. So if I change the identity function by some non-preserving functions, such as some automorphism in KKS, so you know that automorphism just change the index of the coefficient. Then do you think it happens the same effects as the identity function? What do you think about that?
I think there will be no problem on changing such functions, but if you are talking about the programmable bootstrapping,
yeah, that's right. Or just the automatic. So you define the rebel round as an identity minus rebel mode. So then we can redefine some such functions such as automorphism minus rebel mode. So we make a new function, and we can plug this function into the parentheses, and we obtain a new equation, and so the left side is replaced. Left identity function is replaced by some automorphism, and right side is some modification is occurred. But I think the effect. So what I want to know is there is some differences between what I talking and your works. So
as I understand, your question is to comparing your question that this work is another instance of programmable bootstrapping. Am I right?
I think identity function just the role of identity function is it's just my thinking, but just non-preserving function. So it just do that thing. So some non-preserving function. I think the same work because they just preserve the ROM. So there's no error implication. So I think I can change the identity function to some non-preserving function. So such as so there are some famous non-preserving function in CKKS. So the automorphism. So I just curious about there are some possibility to optimize this your ideas.
Yes, I also think that applying such technique on the Iber round is also available, same as the conventional bootstrapping. So Iber round can be applied to the programmable bootstrapping. Yeah.
Okay, thank you.
Any other question from the audience? There was a question online, yeah. So let me get it. Okay, so it's a question by Hilda Vitor Lima Pereira. Please, could you comment more about the column bootstrap bits precision on slide 22? If we start with scaling 2 to the 60, what is the final precision? Okay, so then there is an addition to the question, which is then starting with small scaling factor, what is the final precision?
I'm not remembering the exact value, but it is much higher than the conventional bootstrapping one. It is natural because on this diagram, we only dealt with error of curved slash up, but actually there is some existing rounding of curved slot. And there is a polynomial evaluation error on model reduction. So the blue graph is not exactly evaluated by even mode. So even round defined by the identity minus even mode is not exactly same to the given red graph. So the bootstrap precision will be somehow a little higher to the proposed current proposed evaluation.
I think we can thank the speaker again. The next talk is an online talk.
Hello.
We can hear you, but we don't see your slides yet.
Yeah, okay. Let me try again. Well, I'm not sure. Maybe you could stop this sharing that is going on already. I don't know if this is blocking me somehow.
Okay, just a sec.
Thank you.
We can see your slides. Are you still
See
here?
the slides? Okay, thank you.
And we can hear you. Excellent.
Okay, sorry for the technical problems.
Yeah, sure, no problem. So, okay, so the last talk of this session will be on a paper titled Final Faster FHE Instantiated with Ntrue and LWE. And the talk will be given by Hilder Pereira. Hilder, the floor is yours.
Thank you very much for the introduction. So this paper is a joint work with Charlotte Bonte, Ilya Ilyashenko, Jung-Yoon Park, and Nigel Smart. Please, if there is any problem, you just tell me. You can turn on your microphone and tell me, okay? So the starting point here is essentially a comparison between these two hard problems, the RLWE, the ring learning with errors, and the N-true problem, right? So the ring learning with errors is very famous, and it's used to construct basically most of the fully homomorphic encryption schemes that we have. And what the RLWE allow us to do is to sample pairs of polynomials from a polynomial ring. So we can define these integer polynomials with degree bounded by some parameter n. And then we can sample pairs of polynomials where this second element here has a hidden structure. It actually hides the secret S, but they look uniformly random, right? If we don't know S. But we have a kind of similar problem, the N-true problem, that also allow us to hide a small polynomial into another element of this ring, so another polynomial. And this...
Hilda,
Yes?
just a sec. Yeah, so we were stuck on the first slide. Okay, thank you. So now we can see the second slide.
Okay, if I do this, is it moving?
No. Yes. Yeah, there seems to be some delay. So now we are on the ring LWE and N-true problem slide. Huh?
Yes, okay, thank you.
Okay.
So I was just saying that the N-true kind of give us the same. We can construct this polynomial B, a ring element, that hides this small secret, and at the same time it looks random. But the difference is that for the RLWE, we need a pair of ring elements, while for the N-true, we just have one polynomial, right? So if we could somehow, it looks like these slides are stuck again. Okay, so if we could somehow replace the RLWE problem by the N-true problem, in the FHE schemes, we should, like the intuition is that we would be able to use half of the memory and half of the ciphertext because of, instead of working with pairs of polynomials, we would work with a single polynomial, right? These slides are not passing, right?
We are still on slide number 3.
Yeah, I can
ring
see it
LW
now.
and N-true.
Oh man, this is not good. Okay, I will just try one thing, please. Let me just do this. You are not seeing it, no?
Hilda, do you
Yes.
see how to solve the problem, or?
No, I'm sorry. I'm trying to share, but I click on share and it's not sharing.
Otherwise, I've been told that you gave us a pre-recorded
Yeah.
video. So in the worst case, we can just.
Yeah, maybe it's better. I'm sorry about this. I mean,
Yeah, sure, that happens. Huh? So yeah.
I will stay online. After this, we can answer the questions, at least if people have any questions.
Yeah. Okay. So let's do this. Huh?
Final, faster, fully homomorphic encryption instantiated with N-true and LWE. This is a joint work with Charlotte Bonte, Ilya Ilyashenko, Jung-Yoon Park, and Professor Nigel Smart. So most FHE schemes are based on the ring learning with errors problem. This problem allows us to sample pairs of polynomials from a polynomial ring, so a ring with integer polynomials with degree smaller than some parameter n, and although this pair of polynomials hide the secret value s, they look random. But actually there is another problem defined over polynomial rings, which is well known. It's the N-true problem. And with this problem we can hide a secret polynomial f into one single polynomial that also looks random. So you can see that the N-true allow us to use one single polynomial instead of a pair of polynomials. So if we could somehow replace the RWE problem by the N-true problem in these FHE schemes, the intuition is that we should be able to use half of the memory and maybe half of the running time. And actually, this observation has already been used in the past. So some authors tried to construct FHE schemes using the N-true problem. For example, there was this scheme Yash that was more efficient than the corresponding RLWE-based schemes at the time. But the problem is that the ciphertext modulus, this parameter q, that these schemes based on the N-true used were super polynomial in n. While the first N-true ciphers, they used like N-true encryption, N-true crypt. They used very small values of q, just linear in n. And it turns out that the N-true problem is insecure when q is too big in comparison to n. Now we understand well why this is the case. So before we essentially just knew these q recovery attacks, which have time exponential in n. But there are new attacks called sublattice attacks that whose hardness depends very strongly on q. So the situation is the following: when q is linear in n, the sublattice attacks are more expensive than the q recovery attacks, and then because the q recovery attack is already exponential time, the N-true problem is very hard. But as we increase q, the sublattice attacks becomes easier and easier, and at this point, if q is exponential in n, then the sublattice attack becomes polynomial. So if you have an attack that runs in polynomial time, this means that N-true problem is very easy. So the sublattice attacks become easier at some point it costs essentially the same as the q recovery attack, and this point is called the fatigue point. So new results, especially this paper by Lauduca and Vorden, computed this fatigue point as n to the power of 2.5 essentially. So if we choose parameters with q larger than this, we are in this region, which is known as overstretched. And in this region, the N-true problem is not as hard as we want because of the sublattice attacks. So when we use the N-true problem to instantiate our schemes, we have to restrict ourselves to this region here, so below the fatigue point. So the first contribution of the paper is constructing a scheme that looks like the GSW scheme, but it's based on the N-true, and because of this it has a faster external product. So the external product is the main operation of this type of schemes, these GSW schemes. And then we use this NGS to bootstrap a scheme that is based on the N-true. And then because this scheme is based on N-true and NGS is also based on N-true, this means that we obtain FHE based only on the N-true problem and with parameters below the fatigue point. And also we use NGS to bootstrap a LWE based scheme, and when we do this combination of LWE and N-true give us a bootstrapping that is 28% faster than TFHE's bootstrapping and uses about half of the memory that TFHE uses. So now we'll explain a little about our scheme NGS. So the secret is just the small polynomial from the n-true problem. And then we define two types of ciphertexts. A scalar ciphertext, which is just a polynomial, so we have an n-true sample and we add the message is scaled by some integer factor delta. And the vector ciphertext is composed by essentially a vector of this scalar ciphertext here, but this delta, instead of a single delta, now is a vector with powers of some value b, right? So we have a vector of n-true samples, and then the message is multiplied by the vector of powers of some base. We can choose this base b here, and then L is log of Q in this base b. So in the original GSW scheme, this instead of this vector here, what we have is a matrix like this. So you can see that here we have L again, so 2 times L rows and 2 columns, right? So 2 times L times 2, this means that we have 4 times L elements, and here we just have L elements. Then to run an external product, we just have to take this scalar ciphertext, we decompose it into a vector of L entries, and we multiply it by a vector ciphertext, right? So this is just an inner product. So the external product is an operation between a scalar and a vector ciphertext, and it costs just L multiplications on this polynomial ring. So when we compare it with the GSW scheme, we have this scalar ciphertext now is just one polynomial instead of 2. And the full ciphertext in our case is a vector with L polynomials, while in GSW it's a matrix with 4 times L polynomials. And then the external product is just an inner product in our case, so it just costs L polynomial multiplications. But with the GSW scheme, the external product is a vector matrix multiplication, and then it costs 4 times L polynomial multiplications. Now we will explain how we use the NGS to obtain fast bootstrappings. So we used the framework from FEW and TFHE, which is essentially this. So we start with an LWE encryption of some message M with some large noise E, and we want to obtain an LW encryption of the same message but with a small noise. So what TFHE and essentially FEW does is this. We have a main loop using external products, and this is evaluated with the GSW because the GSW implements the external products. And in this main loop, we are essentially running the linear part of the decryption of this scheme in the exponent of this monomial X. So what we obtain is M scaled message M plus some noise here in the exponent, and this is encrypted under the ring LWE instead of the LWE. And then there is a extraction which takes this M from the exponent and puts it in the coefficient, and also a key switching so that we go from the RLWE back to the LWE again. And then this gives us an LWE encryption of the same message M, but now this noise E doesn't exist anymore. We just have a new noise E prime, which is smaller than the original noise. So this is how TFHE does it. Well, we already have the external products with the NGS, so we can run this part. But when we do this, we obtain a monomial encrypting this same value, but encrypted under n-true instead of RLWE. And then this means that we need somehow to extract and key switch for n-true now, right? And also, if we want everything to be based on the n-true problem, then we need a new scheme based on the n-true instead of the LWE. So we will start with this. We show how we constructed the base scheme based on the n-true. So we used this matrix n-true problem, which is kind of the corresponding of the LWE for the RLWE, right? This is n-true without the ring. So what this M n-true says is that if we have a random, a small norm matrix G and a small norm matrix F, you take the inverse of F and you multiply by G, then you get this matrix C that looks random, just like for the polynomial case, right? Well, but if you take the ciphertext to be a matrix, then to decrypt you have to multiply by the matrix F, and we don't want the decryption to be a matrix multiplication because this is too complicated. We want the decryption to be simple, so just an inner product, vector multiplication, right? So what we do is, instead of considering the whole matrix C, we just take the first row of C and we use this as the ciphertext, right? And if you check it, the first row of C is actually the matrix G times the first column of the inverse of F, right? So now we have a vector of dimension n. And then to decrypt now, we just encrypt the message in the first entry of this vector C. So to decrypt, we just need to multiply by the first column of this matrix F instead of by F, right? So if define this small f here as the first column of F, the decryption now is just this inner product C times F. And then because this is just inner product, we can compute it in the exponent of X using the external products of the NGS scheme. So now the bootstrapping goes like this. We start with an encryption of some message M under this vector small f, and then we use n external products to multiply this vector ciphertext by this secret vector f here. So what we obtain is this monomial, and in the exponent of it we get the error plus the scaled message, right? And this is a normal n-true encryption, so it's encrypted under this polynomial f and belongs to this polynomial ring. And then we run the extraction essentially in the same way as TFHE. So this eliminates this E here, removes this noise E that we had in the original ciphertext, and brings M from the exponent to the coefficient here. And then we propose a key switching for n-true ciphertexts, right? Because this is encrypted under n-true. And we apply this key switching to go back from an encryption of dimension capital N to dimension small n, and also to switch the key from this polynomial f to the vector f that we had in the beginning. So the output has exactly the same format as the input. So it's an encryption of the same message, but with a smaller noise, right? And then we can set all the parameters below the fatigue point. So now we have FHE with fast bootstrapping based only on the n-true problem, right? So we start with an n-true encryption of some message M with large noise E. We use the external products and we get an n-true encryption of this monomial with the message plus some noise in the exponent. And we have the extraction and key switching, which give us an n-true encryption of this same message M again, but with a smaller noise E prime. We also used NGS to bootstrap a scheme based on the LWE. So when we have a scheme based on the LWE, just like in FEU or in TFHE, the ciphertext have this form. So to encrypt a message M under secret key S, we sample this uniform vector A, and then we compute this integer B as the inner product of this uniform A times the secret S. We add some noise and the scaled message, right? All of these modulo Q. So to decrypt, essentially we have to take this public A multiply by S, this is a linear product just before, and subtract from B. So this we can already do using the external products of NGS, right? Then we obtain an encryption of this monomial B minus A times S, which is an encryption of the scaled message plus some noise, and all of this encrypted under the secret polynomial F of the n-true problem. So this means that we already have this first step of the bootstrapping framework, right? We can start with LW encryption of some message M with large noise E. We run the external products using NGS, and we get an n-true encryption of this power of X. Now, to go back to LWE, we proposed a key switching that switches from the n-true to the LWE problem. So we run the extraction as before. This gives us an n-true encryption of M and removes this E. And then we run this new n-true to LWE key switching to switch from an encryption of M under n-true to an encryption of M under the LWE problem. And this closes the loop and completes the bootstrapping procedure. So now we are going to see the practical results. We implemented everything in C++, and this implementation is publicly available, so you can go to this GitHub repository and download it and install and play with it. And because we mainly wanted to compare with TFHE, which is the state of the art for binary circuits, we used the same FFT library as TFHE, and then we compiled our code with the same compilation flags as TFHE, and we tried to use similar parameters as the ones used in TFHE. So we have two FHE schemes now. We have one that is based on n-true, that we call M and true here, and one that is based on the LWE, right? And then we bootstrap both of them using NGS, which is based on n-true. So these are the parameters for these base schemes. So the dimension of the ciphertext that we want to bootstrap with n-true is 800, and with LWE is 610. So for TFHE, they use LWE ciphertexts, and then the dimension is about 600 as well. And for the NGS, the degree of the polynomials that we have in the polynomial ring is always 2 to the 10 in our case. And what changes essentially is the decomposition base from one case to the other. And for TFHE, this dimension here is also 2 to the 10. So this means that our FFTs, the Fourier transforms, are over the same dimension as in TFHE, right? So they are really comparable. And we have to remark that this value n here, this tells us how many external products we have to run. So the thing is, for M and true, we see that we have 800. This is much more than in the LWE case. So even if each of our external products is cheaper than in TFHE, because we have to run much more of them, at the end our M and true scheme is slower than the TFHE. But for the LWE case, because the number of external products is similar to the TFHE case and each external product is cheaper, then our LWE with n true is faster than in TFHE. So when we run TFHE in our experiments, we got that each bootstrapping takes around 66 milliseconds. And then for our MN true, we got 92. So this is kind of similar, same order of magnitude, but slower, right? But our combination of LWE and n-true runs the bootstrapping 48 milliseconds. And we can see here that that's the main reason, because the number of FFTs is much smaller in our case. So essentially what we got is that if you check here, the bootstrapping key and the key switching key, they are much smaller than in TFHE. So the key material that we need is about half of what TFHE needs, and the bootstrapping time is about 28% faster. So to conclude, we proposed an FHE scheme based on N-true with parameters that lie below the fatigue point, so outside of the stretched regime. And so this brings back N-true FHE to the game, and we hope that this result will bring more attention of the academic community so that people can do further research on N-true based FHE and maybe improve the efficiency of our scheme or create new schemes based on N-true. And well, we proposed this scheme that looks like GSW, but is based on N-true, so we called it NGS, and it has a smaller ciphertexts and faster homomorphic multiplication when compared to the RLW-based GSW. So we hope that this NGS will also be useful for other applications. So essentially where GSW is used, maybe we can use NGS instead. And finally, we proposed this FHE scheme mixing N-true and LWE. And we saw that this runs faster than TFHE. So that's all. If you have any questions or comment, please feel free to contact me. And thank you all.
Okay, so we are running late, and the attendees from the other room are starving in front of the food. So if there is a quick question, we can take it, but otherwise, I suggest we do it offline. Any quick question? Okay, so let's thank Hilda again.
Thank you very much.
The vegetarian options are, I mean, there are more vegetarian options